I think this is my third time, and it is really nice to be back and then see some the old friends, and also, the young people. I see many young people, young faces, and which shows, I think, the group is growing well, so I'm very happy about that. All right, so today I'm going to talk about partitions associated with three third-order Mach zeta functions, and this is my talk is based on joint work with George Andrews and Arthur Dixit. Okay, so I think some of you are familiar with partitions, but some maybe not. So let me first start by defining the integer partitions.
Okay. 아래쪽에 있는 것 같아요.
아래, yeah. Yeah, thank you. Okay, so a partition of a positive integer n is a non-increasing sequence of positive integers that sums to n. So, for example, I like always examples. Okay, so when n equals to 4, there are 5 partitions. Okay, so 4, 3 plus 1, 2 plus 2, and 2 plus 1 plus 1, and then 4 ones like this. Okay. And we denote the number of partitions of n given n by p of n. Okay, so in the previous example, p of 4 is 5. All right, okay. And p of n plays an important role in the theory of partitions as well as number theory. And it has very rich arithmetic structure, and one of them is the following. Oh, okay, so before we move on to that, let me first of all introduce the generating function of p of n. Sorry about that. So let's recall the partitions, 5 partitions of 4. Okay, so here 4, and then these partitions, and then I color these 3 in different colors, blue and the red and the yellow. So you might notice that these are actually these numbers, we call them parts, and these partitions have parts n most 2, less than or equal to 2. Okay, so to show how we derive the generating function of p of n, let's first restrict the size of the part. So in this case, in this example, I'm taking the parts up to less than or equal to 2. So let me denote the number of such partitions by p sub 2 of n. So p sub 2 of 4 in this case is 3. So these 3 colored partitions. Then the generating function of this p2 of n, in other words, we are interested in this formal power series, infinite series, p2 sub of n q to the n. We can derive this one by taking the product of these 2 infinite series. The reason is, for example, when n equals 4, think about the possible ways to get q to the 4th power. Okay, so the red one, 2 times 1, and then this 1 times 2, the product of these 2 corresponds to this partition. Sorry, yeah, 2 and then 1 and 1. So these 2, the first one indicates how many ones. Okay, so 2 ones there, and then 1 times 2. This one indicates 1, 2. All right, and then this blue one, 2 times 2, gives us this partition, and this yellow ones, this one corresponds to this power. So q to the 4 times 1 times q to the 0 times 2, which is just 1. So we get the generating function of p2 of n is indeed 1 over 1 minus q, and then times 1 over 1 minus q square. And actually, when the absolute value of q is less than 1, we already know this one is well defined in terms of as a function, right? Not as a formal power series. Anyhow, now to consider all the parts, we take just the limit. So here, instead of 2, we take k, and then let k go to infinity. So in other words, we have this generating function, p of n q to the n is 1 over this infinite product. Okay, all right, so we're good, I think. And as I mentioned before, this P of n, this partition function, has very rich arithmetic structure. Okay. And first one is this following congruencies. So 1919, Indian mathematician Ramanujan proved these three congruencies: mod 5, 7, and 11, P of 5n plus 4 congruent to 0, and then 7n plus 5 congruent to 0, and then 11n plus 6 congruent to 0. And besides these congruencies, he also, with Hardy, used a circle method to find a symptotic expansion for P of n. And later, Rademacher, he is the advisor of George Andrews. Rademacher obtained the conversion to infinite series representation for P of n. So I didn't put actually the infinite series for P of n on my slide, but you can easily find the expression in the theory of partitions by George Andrews. Okay, so there. And besides partition functions, I didn't mention, but here in the generating function of partitions, sorry about that. If we take the reciprocal of this one, in other words, 1 minus just the bottom one, 1 minus q, 1 minus q squared, 1 minus q cubed, etc., then this one is one of the classical Jacobi set functions. Okay, and Ramanujan introduced Mach zeta functions. They are not zeta functions, but pretty much similar, but its behavior is really different. Okay, so anyhow, Ramanujan introduced Mach zeta functions in his last letter to Hardy in 1920. So what is a Mach zeta function? He didn't explicitly define, didn't give any definition, but he mentioned like this: a Mach zeta function is a function of the complex variable q defined by a q series of a particular type, Eulerian form, okay, which converges for absolute value of q less than 1 and satisfies certain conditions. Actually, there are 3 conditions he gave in his Lowe's notebook. But I didn't put them because they are more technical. But the thing is, absolute value of q less than 1, it behaves well, but on the unit circle, its behavior is really strange. Okay. And then he gave a number of examples, classifying them by orders, so order 3, 5, and then 7. And during the past few decades, many mathematicians, including George Andrews and Dean Hickerson and Yun-Seo Choi and others, tried to understand the Mach zeta functions and their relationships given in Lowe's notebook. Okay. Okay. Modern definition of Mach zeta function. Okay. Actually, about 15 years ago, in 2001, Sander Zwergers, he developed a theory actually that explains Ramanujan's examples in terms of modular form and then other theories. And due to his work and also extensive work of Canono, Catherine Brinkman, and many others from his group and her group, now it is known that Mach zeta functions are essentially the holomorphic parts of a weight 1/2 harmonic weak mass forms. It's crazy form, I guess. Yeah. All right. So this is the modern definition, and so from number theoretic point of view, they study Mach zeta functions in this way. Okay. And also, like zeta functions, Mach zeta functions arise in many areas. For example, L function, Lie theory, basic hypergeometric series, etc. So I listed a few. All right. Okay.
How could they use for cancer research?
Yeah, right. But I mean, because Q series arises in statistical mechanics, so I mean, there's some as an application in physics, and then Mach zeta functions also arises in the string theory, something like that. So that is not my specialty, so I don't know very well, but yeah, it has lots of applications. All right. All right. Okay. So, okay. All right. So we saw lots of, possible applications in other areas, but we want to focus on more partitions and the relationship within the theory of partitions. So before the Zweger's discovery, actually, partition theoretic interpretations of various results involving Mach zeta functions have been the subject of intense study of many decades. So, for example, George Andrews and then Garban, there are about 10 identities, okay, more than 10 identities involving Mach zeta functions, and especially George Andrews and then Garban reduced the known proofs of these identities based on the rank function of a partition and the smallest part function. Okay, so here, yeah. And actually they made a conjecture, and these conjectures are known as Mach zeta conjectures, and they are first proved by Dean Hickerson in 1988. Okay. Right. And also another approach to understanding Mach zeta functions in the theory of partitions is the following. Okay. Mach zeta function itself also admits a simple and interesting combinatorial interpretation. So for instance, we consider this Mach zeta function. It is one of fifth order Mach zeta functions of Ramanujan. And here, look at this infinite series, we have q to the n over this product. And from this, we can take this n to be the smallest part of my partition. Then at the bottom, we can have n up to 2n minus 1. In other words, we have restrictions on the parts. The part size is up to less than twice the smallest part. Okay. So I put here easy to see, but some of you, to some of you, it might not be easy, but as I explained, because this n indicates the smallest part, then taking the geometric series expansion of the bottom one, we can see that it is the generating function for partitions where no part is as large as twice the smallest part. Okay, all right. And there are few other Mach zeta functions in this group. Okay, all right. Then recently, Andrews and Dixit and myself considered this new partition function, P omega of n. This one denotes the number of partitions of n where we have these restrictions. In each odd part is less than twice the smallest part. So when we have this kind of number, counting function, then the first question is what is the generating function, and then does it have any interesting properties? Okay, so before we go into that, let me give you an example. So here I listed 11 partitions of 6, and then I also colored the sum of them, actually 8. Okay, then this one, the uncolored one, 5 plus 1. The smallest part is 1, and actually the odd part of 5 is way too large than the smallest part. And actually this one is larger than twice the smallest part, which is 2. So we just cancel out, okay? And cross out. And then 3, 2, 1, the smallest part is 1, and twice the smallest part is 2. Unluckily, we have this 3, so we cross this out, the same thing. But all the others will survive. Okay, so by p omega of n, by this partition function, here n is 11. So p omega of 11 is 8. Okay, then what is the generating function? Generating function is this one. Why? Because for the same reason, Qn, this n indicates, corresponds to the smallest part, and 1 over 1 minus q to the n, we might have more than one smallest part, and q to the, the notation. Okay. Yeah, so here is the q series notation. I try to avoid this notation because, you know, people who are not familiar with this don't like this one. So, but sometimes I cannot avoid them. So yeah, A semicolon q sub n is this rising factorial, q factorial, and then infinity is this one. Okay, so back to this generating function, the bottom one, q to the n plus 1 semicolon qn. From this, we have n plus 1 up to 2n. So there is no restriction. In other words, we can have any numbers between the smallest one up to 2n. However, after that, we have only even numbers. Okay, so so that's why the generating function of p of w, p sub w of n, the number of partitions where what? All the parts less than twice the smallest. So no other larger than twice the smallest appear in my partitions. Okay. All right. Now we have this nice infinite series. Then the next step is, what are the coefficients? The coefficients have any interesting properties. So we just go on to computer, so like Mathematica or Maple or MATLAB, whatever, and then take some, take the expansion of this series. Okay, so these are the coefficients. Okay, then what can we do with this coefficient? Next one is, are they counting anything already known? Okay. So here is a good reference. We go online this time. So yeah, online encyclopedia of integer sequences. So if you have some sequence you are interested in, then just plug in the coefficient. So like these values, I put up to 18, and then search. Push the search button, that it will show you some sequences that are already known. I think probably registered in this website, okay? And the first one, look at this. There are 7 sequences that match these numbers. And the first one is the coefficients of the third order Mach zeta function, omega of q. So that's why in my partition function, here we have the suffix p sub omega. Okay? All right. All right.
But they have also have a
Yes.
generating function there.
What?
Is that the same generating function in the first?
No, it's not. Okay, so if that is the same one, then we don't need to go on online because we already recognize it. So yeah, but the representations are different. However, they are counting the same thing. Does it answer your question? Okay. All right. So then what is the third order Mach zeta function, omega? That is defined in this way by Watson, G.N. Watson, and actually later discovered that Ramanujan knew this one, and then he written down, actually. He had written down in his Lowe's notebook. Anyhow, so this is third order Mach zeta function, and the computer search tells us what? This infinite series equals what? The other infinite series I showed you in the previous slide. Okay, so we got the conjecture, and then all we need to do is to prove it. Okay, so we proved it using Q-series identities. The proof is a little intricate, so I'm not gonna go into that. I'll just skip it. And we showed this generating function, not exactly omega of q, but differ by q. So q times omega of q. So the coefficients are shifted by 1. All right.
Is it a combinatorial? I mean, do you know combinatorial proof, or is it?
No, there is no combinatorial proof. So yeah, actually that is one of my
Okay.
my question, open question. Okay, so okay, all right. And actually, we can find some work in the literature on the omega function. So, I mean, Sharon Garthwaite, she obtained an exact formula for the coefficient of omega of q using the heavy theory of modular forms and Poincare series. And also, that formula is an Hardy and Ramanujan Rademacher type exact formula for P sub omega of n. Okay, and also like the congruencies for partition functions P of n, Garthwaite and David Peniston, they showed there are infinitely many arithmetic progressions a_n plus b such that P sub omega satisfies this congruence mod m. Okay, but their theorem actually is about existence of such arithmetic progressions. They didn't give any explicit arithmetic progression congruencies. And recently, I think about 4 years ago, 2011, Matthias Walder proved the first explicit congruencies for a piece of omega of n. Okay, and these were they were the smallest ones. So mod 5, 40n plus 28 congruent to 0. Okay. However, yeah, their method. I mean, his method. His proof is based on, the heavy machinery of a modular form, and then the modern, the modern method techniques. But back to the coefficients of piece of omega, we can easily identify other congruencies. So we are back to coefficients of omega of q. So these are the coefficients. Okay, I added a little bit more, so up to 40. And first of all, look at this. The first one is odd number, and then the third one is odd number, and all even up to 10, q to the 10, and the 29 is odd number. And then all even, and 17 odd, all even, and where is odd one? Here, 33. Okay? So this says, actually, if we reduce this infinite series mod 2, most of terms will go away. Even terms will go away, and then it is actually congruent reckoner series. In other words, majority of the coefficients are 0, and then only the non-zero terms are very sparse. Okay. And furthermore, I highlighted these coefficients, 4 times q to the 4, clearly divisible by 4, and 36 divisible by 4, and then 176 as well, 660, and then these coefficients are all divisible by 4, and look at the powers, 4, 12, 20, divided by 8. So 4n plus 8. So we can make a conjecture. P sub omega of 4n plus, 8n plus 4 congruent to 0 divisible by 4. Okay, and also you can you might notice this 8q6 divisible by 4, and then this one 56 divisible by 4, 284, and then this one, they are all divisible by 4, and actually they are divisible by 8. For mod 8, I don't have a theorem because while preparing this slide, I realized that actually they are divisible by 8. So I don't know about that, but at least mod 4, besides mod 2 congruence, we have this congruence is for this partition function, P sub omega 8n plus 4 congruent to 0 mod 4, and then mod 4 and then mod 4. Okay, all right. So how do we prove this? Before we move on to the proof, actually, and we noticed this, and while we were proving these congruences, actually, we realized that we can establish an infinite series of congruences using induction with this one as base case. So here is the theorem. So this one is congruent 0 mod 4, and then mod 4. So the previous one were the case when k equal to 1. Okay, all right. Then how do we prove? The key identity is this Q series identity. All right, here you can compare both sides, and then actually we are interested in Q to the 8n plus 4. And you see on the left hand side, you don't get Q to the 8n plus 4 from here and then from here. So Q to the 8n plus 4 comes from only this one. So the coefficient of Q to the 8n plus 4 here matches the coefficient of that power on the other side. And the nice thing about this one is an infinite product, and it is much easier to handle than the infinite series. Okay, so using this key identity, we were able to prove the congruencies. All right. Okay, now let's switch our focus to SPT function, smallest part function. Okay, in the earlier slide, I mentioned Mach zeta functions and rank, and then smallest part function. Actually, we before George Andrews, some people knew that there was some relationship between smallest part function and then rank generating function and Mach zeta functions, but it was George Andrews who first studied systematic study the smallest part function. So what is the smallest part function? Okay. SPT of n, so S stands for smallest, and then P stands for part, and then PT stands for part, okay, of n. This one counts the total number of appearances of the smallest part in all of the partitions of n. So for example, here we have 5 partitions of 4, and then I underline the smallest parts in each partition. So 4, and then here 1, and then here there are 2 smallest parts, and then there, and then there. Instead of counting each partition by 1, we count all the smallest parts. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So SPT of 4 is 10. So it counts partitions, integer partitions, but with a different weight. Okay. And and surprisingly, it turns out that the SPT of n, like the partition function P of n, it has very rich structure in arithmetic structure. Okay, So first of all, Andrews proved the three surprising congruencies for SPT of n, which is an analog of the congruencies for P of n. So mod 5, 7, and 13. So here, as you see, we have, yes, we have 5n plus 4, 0 mod 5, 7n plus 5, 0 mod 7. Actually, P, the partition function also satisfies this congruence. Okay, but unlike partition function, SPT function has congruence for mod 13, not 11. So this one is a little bit different. The reason is, you will see in a moment, this SPT function is related to rank function. The rank function is the, when you are given a partition, the rank of that partition is the largest part minus the number of the parts. Okay, and that is the combinatorial, I didn't mention, but that is the combinatorial statistic for the, that actually accounts for the congruences of mod 5 and the mod 7. Okay, so if you, according to the rank, if you classify partitions, then you can actually divide the partitions into 5 equal classes or 7 equal classes. So that indicates, that proves the congruence is mod 5 and the mod 7. So actually SPT function, the smallest part function, has some relationship with the rank. But the reason we don't see mod 11 is because the rank does not work for mod 11 for partitions. Instead, crank works. So that's why we don't have SPT 11 and plus 6 here. Okay, so, all right. Okay, so to see the relationship between the SPT function and then the rank function, we need a generating function of SPT. Okay, so what is the generating function? Then here, the generating function of SPT is the following. The only difference is the first infinite series in the summand. So instead of Qn plus 1 plus Q to the n, Qn plus Q to the 2n and just Q to the 3n, we need to count the occurrences, appearances of smallest parts. So that's why we have a 1, 2, 3, and then 4, etc. And then for the other parts larger than the smallest, we count them, their weight is just 1, right? So we have this ordinary geometric series expansion. So the generating function of this one is Q to the n here, n indicates the accounts for the smallest part, and 1 over 1 minus Q to the n square, we have, it comes from this infinite series. And the remaining goes here. Okay, so this is the generative function. So SPT and then just ordinary partition function, the only difference is we have 2 square. Here, without square, we go back to the generative function of the partition, P of n. All right. Now, this generative function has another representation given by as a special case of Watson's Q analog of Whipple theorem. I'm not going to introduce it. It's very complicated. So anyhow, there is a nice identity, and then using it, we can prove. Right. So this allowed him to prove SPT is related to the partition function P of n, and the second Atkin-Garban rank moment N2 of n by in this way. Okay, so here n is just the number, that given number, and then p of n, that partition function, and then 1/2 n2, capital N2 of n is the second rank moment. In other words, we take all the partitions with weight, rank, square of the rank. Okay, all right. Then, can we do the same thing with the partition, our partition function p sub omega of n? Okay, yeah, he used the, right, the SPT congruencies. All right, so we can define SPT sub omega of n because by just scoring the smallest, the factor that gives us the smallest part. So what I'm saying, where is the, sorry, I think I didn't put that, but the, sorry. So p sub omega of n, sorry about that. I have to go back. Yeah. This is not this one, we are not taking this one because the sum and the n, q to the n square plus 2n, this expression is not good enough because it doesn't classify our partition according to the smallest part. However, this expression, okay, is q to the n, this n indicates the smallest part, and then we have 1 over 1 minus q to the n, so the weight is just 1. But we want to give the different way, the number of the occurrences of the smallest part. So the generating function of SPT omega is just what? The same, and then score this factor. So 1 minus q to the n square. That is the generating function. Okay. Yeah. All right. So, for example, I put an example here. So n is 6, and these are the partitions counted by p sub omega. So omega of 6. Okay, and then I underline the smallest part, and then just count the number of the underlined parts, and which is 21. Okay. All right. And then we were able to show actually this SPT omega has some arithmetic properties like this. Okay, so it doesn't have mod 7, mod 13, or mod 11. We have no idea, but we just did computer search. In other words, we looked at the coefficient up to 400 over 1000, and then try to extract any interesting properties, and we got only mod 5. Okay, so but good enough. At least we have 3 congruencies. So mod 5, SPT 5n plus 3, and then 10n plus 7, and then 10n plus 9. And actually from this we get a sub-arithmetic progression. In other words, 10n plus 8 when n is odd. So we have actually 10n, mod 10, 7, 8, and 9. The coefficients are all divisible by 5. Okay. All right. Yeah. Oh, here is the generating function. Sorry about that. Yeah. So we have the score here up here. Okay. Then how can we prove this? Again, in the hierarchy of a Bayesian hypergeometric series, it starts from 1 phi0. You don't need to know about what something phi something, but there is 1 phi0 and then 2 phi1, etc. So we can go up to any n phi n minus 1, but actually a phi 7, that is one of the nicest one, and then the above it, we have this Bailey's 10p9 transformation. Okay, so it is just Q series identity. All right, so 10p9, the left-hand side gives us an infinite series, and then that infinite series equals this infinite product times another infinite series. And we don't usually use the whole thing. Instead, we make some appropriate change of variables and then try to derive something nice. Okay, so here we take the second derivative with respect to z on both sides, and then let's z be 1 to get this one. Okay, then I skipped all the steps, but the 10p9, that one, just a second. Yes, from this side we get the from this side we get the SPT function, the generating function, and we move this thing to the other side and then make us change of variables. Then from this we get this one. So lots of work between to get from the previous slide to get to this. Okay, so anyhow, this one is 1 over q square sub infinity. It is the generating function of partitions where the power of q raised to 2. So q replaced by q square. So we can identify what it is. And this one is related to the divisor function. And this one is actually the second rank moment. Okay, so we know about the second rank moment, and then here q is replaced by q square. So actually when q is just q, then we know mod 5n plus 4 is congruent to 0. But now q is replaced by q square, so we multiply by 2, then it reduces to, because 4 times 2 is 8, which is 3, so it reduces to mod, the 5n plus 3 mod 5. So we know that coefficient is a multiple of 5, so it goes away. And then we only need to take care of this one. Take care of this one. And Cn, let me call the coefficient of this side Cnq to the n. Then using some Q series manipulation, okay, let me skip all the steps, and then we are able to show actually the coefficient 5n plus 3 is divisible by 5, and then this one is divisible by 5, and this result in is these three congruences. Okay. All right. In my talk title, I mentioned 3/3 order Mach zeta function, but we saw only one. So there are 2 more. And it is a variation of the omega function. Okay. So p sub nu of n, here now we are given a partition. Then another set of interesting set of partitions is the partitions into distinct parts. So with the same restriction, each odd part is less than twice the smallest part, but we don't allow repetition, so distinct parts. And then we call the counting function p sub nu of n. So, these are the partitions counted by p sub omega when n is 6, and only these 2 partitions are counted by p sub nu. All right, so 2, and actually we were able to show this one, the generating function of P nu of n is indeed nu of minus Q. Nu of Q is one of the third order Mach zeta functions of Watson and Ramanujan. Okay, so yeah, and instead of then each other part, can we add restriction on even part? Yes, we can do that. So yeah, I mean and also this, we can define the SPT nu of n, the SPT function associated to nu function, and then in this case, because all parts are distinct, so the smallest part function is the same as the partition function, and we have this nice congruence, and we can prove this using this identity. So actually, nu and then omega are related in this way, so we can get some result for nu out of this. Okay, all right. And yeah, back to the the different restrictions. In other words, this time we restrict on the even part. Okay, so everything is the same, but here each even does not exceed twice the smallest part. So here is the generating function. So we have a Qn, q to the n plus 1 QQn, and then we have this one. Then it reduces to actually the generating function of the partitions into distinct parts. So minus QQ sub infinity. So we don't allow repetition here. So we are able to prove this one. And how about this thing? Yeah. So this time, the same restriction on the even part, but we don't allow repetition. So distinct parts where each even part is less than twice the smallest part, then now we can easily identify the generating function as this one. So q to the n, this is the smallest, and then minus, sorry, there is a typo. There is no q here, okay? So minus q to the n plus 1 qn, and then this one, and this one has this another representation that involves another third order Mach zeta function phi of q. Okay, all right. Okay, then in earlier I mentioned mod 2 properties of p sub omega. There we saw many majority of the coefficients are even. So if we take mod 2, then they will go away. And such property is also very interesting, because here is the Euler's pentagonal number theorem, which is one of the classical partition theorems. So it states that if we take this infinite product, so 1 minus q square, etc., and then expand, then most of the terms will go cancel out, and only these terms will survive. So minus 1 to the n, q to the n, 3n minus 1 over 2. And then there is a well-known Franklin involution that explains this identity combinatorially. Okay. So here, instead of a minus QQ sub infinity, we have a QQ sub infinity. In other words, we assign a minus sign to each part. So actually this one counts if we, yeah, I think I put that here. Yes. So if we, yeah. Here, if we expand this infinite product, then because we assign a negative sign to each part, if we have an even number of parts, then the sign of that partition is positive. And if we have an odd number of parts, then the sign of that partition is negative. And this identity tells us lots of cancellation, and only for when n equal to j times 3j plus minus 1 over 2, except for this one, those two sets with plus sign and the minus sign, they are equinumerous. Okay, so dE of n counts the partitions with an even number of parts, and dO partitions of with an odd number of parts. Okay, so there is Franklin's involution, combinatorial proof of this one, but I'm not gonna go into that because, yes. All right, okay, then we adopt this idea and we assign a negative sign to each part in our partition counted by the piece of omega of n. So the generating function was Qn and there was no negative sign. In other words, 1 over 1 minus Q to the n. So if we actually expand it as a geometric series, then we don't see any negative one. However, we have instead 1 over 1 plus Q to the n. Then in the geometric series, the sign alternates plus 1 minus, etc. Okay. Then, surprisingly, this one, this series equals this thing. So most of the terms will go away, most of the partitions will go away, and only one partition survives for n, which is equal to 6j squared plus 4j plus 1, or 6j squared plus 8j plus 3. I looked up these numbers. The reason we call this pentagonal number theorem is because this number j3j plus minus 1 over 2, these numbers are called pentagonal numbers. And then I looked up these numbers online, and then I found actually they are there, but I forgot the name at this moment. But you can easily Google them and then figure that out. So it counts something. All right. So here is the partition theoretic interpretation of this identity. So here we are focused on only the partitions counted by piece of omega, and then dO of n, the number of parts, and dE of n, even number of parts. And then we took the difference. Then it is always 0 or minus 1 to the j if n is equal to this one or n is equal to this. Okay. So we proved this one based on the Q series manipulation. So there is no combinatorial proof of this one at this moment. All right. Okay. So before I finish my talk, okay, this is my last slide. Then I have a couple of remarks to make. So, first of all, I should mention Frank Garban and Chris Jennings Sharper. He is a student of Frank, and then actually you might have heard of the crank function, the Frank Garban and then Dong-Soo Kim and Dennis Stanton. They discovered the crank function that accounts for the mod 11 congruence for partition function P of n. Okay, so he is that Frank Garban. Okay, anyhow, he is at University of Florida, and he and his students wrote a series because Frank Garban, he is pretty much interested in rank and then crank, and as I showed, the SPT function has some relationship to rank function. So he studied a lot on SPT functions, and recently with his student he wrote a series of papers on analogs of Andrews SPT function. And actually our SPT, the omega of n, is on their list. However, their motivation is different from ours, and also they didn't realize the actually piece of omega of n. Okay. And the second one is, Professor asked about combinatorial proof. Yes, this is my open question. Any combinatorial explanation between the odd Dolby symbol, what is it? I will explain in a moment. And the partition interpretation. Oh, here is the typo. Interpretation presented in this talk. In other words, restrictions on the odd part. Okay, so odd part can go up to twice the smallest part. So then what is the odd Dolby symbol? Okay. So sorry, I should. Oh. Sorry. Where is it? Okay. Sorry about that. Here. Look at this omega function. Actually, we have q to the n square plus 2 times n. If we add, multiply this omega, because in our theorem we are looking at not omega, q times omega. So we multiply this thing by q, then we have 2n square plus 2n plus 1. It's getting complicated. Let's just ignore this part. And then we have 2 times n square. Then we have a Dolby square. Yeah, Dolby square. And then each box is filled by 2, not just 1. Okay? And then we spread out this 2n plus 1 around the Dolby square, filling, by 1. So anyhow, it is related to Dolby square. And 1 over this q, just ignore this q, and then this one increases by 2. In other words, we are looking at only the even part, even numbers as a part. So it has a nice combinatorial interpretation. If you want to know more about that, just let me know after the talk. So anyhow, and then we call that statistic Dolby symbol. Okay, it was studied by Andrews in his paper, I think, about 6 or 7 years ago. One of his inventionist paper. Okay, so anyhow, it was studied by him. So it has its own partition theoretic interpretation, and we have this nice partition theoretic interpretation for this infinite series, but we don't know how to relate them. So, yeah, combinatorially, it could be a good, the problem to go from here to here or the other way. So, okay. So that is my second comment, and also the model 2, the Franklin type. Sorry. Yeah, this one. Can we prove this one combinatorial way? In other words, can we establish a Franklin type involution so majority of the partitions are cancel out, and then we're left with this partitions counted by the partitions of this number. Okay, so here is my last. Is there any combinatorial proof of this identity? And I don't know yet. All right. Then there are more questions around this topic, but let me just stop here and. Oh, thank you.